structural isomers for C4H8O. So we know this will include what? Aldehydes and ketones. Yes. Now you need to make structural isomers. So you got to make chain, positional and functional group also, because aldehydes and ketones also have functional isomers. So let's make the first one. The first one we make, let's make a 4-carbon aldehyde. Yes. Can we name this? How will we name this? I will repeat again. Naming is pick the longest chain or the parent chain. How? You will go from one end to the other end, picking the longest carbon chain or the parent chain, including all functional groups that are attached to it. So this is your longest chain. Now you number your carbon atoms in such a way that the most important functional group gets the least number. So your aldehyde is the most important. It should get the least number. So carbon 1, 2, 3, 4. And now you name it. So this will be what? You have 4 carbons in the main chain. So this will be but. All carbon-carbon bonds are single. That's why this will be an, butan, 1-al. Or you can just say butanal. If something is on carbon number 1, you don't really need to specify the number. But if it's on any other carbon, you have to specify. So it's better that you even specify on carbon number 1 so that you stay in the habit of practice of naming. While naming, you number it, right? So this right here becomes what? Butan 1-al. Now, let's shorten the chain. Let's shorten the chain and make the chain of 3 carbons. Let's keep the aldehyde. Now, aldehyde cannot be on any other carbon except 1. Do you understand that? Aldehyde will always have to be on the corner. You can't put it in the middle of the molecule. You can't be like, oh, let's make a positional isomer of this. Let's change the aldehyde from carbon number 1 to any other carbon. That will not happen. Let me show you why. So if you try to change it, you're going to be like, oh, what do we need for an aldehyde? For an aldehyde, you need a carbonyl carbon with carbon on one side and hydrogen on the other. So you can't make it like this. Do you see that? Why? Because hydrogen can only make 1 bond. So if you make it like this in the middle, hydrogen is making 2 bonds, which is not possible. So aldehyde has to be in the on the terminal ends always. All right. So you can't put it in the middle. So now you shorten the chain. You make the main chain of 3 and put the aldehyde right here on the first carbon. Now you have the 4th carbon. Where will we put the 4th carbon? We will put it as a methyl on any carbon except the terminal. I told you don't put it on the terminal because the longest chain will then again become what? 4, right? So don't put it on the first and the last. We will put it on any other carbon but the terminals. So we've put it here. Now let's pick the longest chain. What is the longest chain of carbons? 1, 2, 3. Either you pick this or 1, 2, 3. This becomes the longest chain. So this right here is your parent chain. Either way, whichever chain you take, the naming will be the same, right? I'm taking this one. Main chain has how many carbons? 3. Which will get the least number? Aldehyde. Remember, I gave you the list of importance between an alkyl and an aldehyde. What is more important? Aldehyde. So it should get the least number. So this will be carbon 1, carbon 2, carbon 3. And this will be called what? On carbon number 2, we have a methyl. So what will we call this? 2-methyl. And then main chain has how many carbons? 3 carbons. So 2-methyl propan 1-al. Do you guys understand this? See, do you see both of these have the same molecular formula but different structures? Their names are different. That means they are isomers of each other. Yeah. Now, so which kind of isomers are they? Structural, yes, but which type? Chain isomers, because in the first one, the main chain is of 4 carbons. In the second one, the main chain is of 3 carbons. So they are chain isomers of each other, right? Now let's see the third one. Let's try to make a ketone. Because aldehydes can also have a ketone as a functional isomer. Let's make this. Can we name this? What's the name of this? Main chain, 4 carbons. What will we call this? But. All carbon-carbon bonds are single. That's why an, butan. And on carbon number 2, you have a ketone. So this will be butan 2-on. Can you have a butan 3-on? No, because when you put it on carbon number 3, you will start numbering from the right. And it will become butan 2-on again. Now you'll be like, oh, miss, let's shorten the chain for the ketone. Can we do that? Let's see. So if you have a ketone, let's say, You'll be like, okay, miss, let's shorten the chain, make a chain of 3. Now, where will you put the 4th? You can't put it on the terminals. You'll have to put it here, but you can't put it here because the carbon then will have 5 bonds. So this is not possible. So that's why we only have 3 isomers for this. This and this are chain isomers. This and this, functional isomers. This and this, chain and functional both. Do you see the chain is different and they are functional too? Yes? Is this clear? Understood? Let's now see C4H8O2. Now you have 2 oxygens. So you'll be like, oh, it could be 2 alcohols, maybe 2 OHs, or acid, or ester. So if you think of 2 alcohols, let's say this. 2 oxygens, 4 carbons, 2 hydrogen, 3, 4, 5, 6, 7, 8, 9, 10. So it should be C4H10O2. So definitely it's not 2 alcohols. Clear? So this is going to be what? Acid and ester. Let's see. So now the first one we'll make will be a 4 carbon acid. Can you name this? Can you name this? This is an acid. Butanoic acid. So this is a 4 carbon acid, butanoic acid, or you can call it butan 1-oic acid because the acid is on carbon number 1. Acid is the most important functional group. It will always get carbon number 1. Now, just like you could not put aldehyde in the middle of the molecule, acid will also never come in the middle of the molecule. Let's see why. So if you try to put the acid here, you can't do that. Hydrogen is again making how many bonds? 2. Can't do that. You can't have hydrogen make 2 bonds. So acid has to be on the terminal carbons. Is that clear? Now let's shorten the chain. Let's shorten the chain, make the chain of 3. And put the 4th one over here as CH3. Can you name this? 2-methyl, because on carbon number 1 you have the acid. On carbon number 2 you have this 3. So this will be 2-methyl propan 1-oic or propanoic acid. Very clear. Now you'll be like, oh, miss, let's further shorten the chain. Make a 2 carbon. Now if you make a 2 carbon, the 3rd and the 4th will have to come here. Now this is not 1, 1 dimethyl ethanoic acid. No, the longest chain is 3. This is again what? 2-methyl propanoic acid, which you've already drawn. Is this clear? Do you understand that? So this is not an isomer because you've already drawn it. So there's no further shortening the chain. Do you agree? Yeah. But now we can make what? Functional isomers. Which ones? Esters. So let's make esters with the formula C4H8O2. 4 carbons, gotta make esters. So let's make esters. We know ester is made of aldehyde, acid and alcohol. So I can take a 2 carbon acid, a 2 carbon alcohol. I told you how to name esters. Everything after the C single bond O comes from the alcohol and is written first. How many carbons do you have after the C single bond O? 2. So we will call this what? Ethyl. And then how many carbons do we have before the C single bond O? 2. So that means 2 carbons come from acid. So this is ethyl ethanoate. And this you see is an ester group. Clear? Now what can we do? We can, so this was 2 carbon acid and 2 carbon alcohol. Can you make a 3 carbon alcohol, 1 carbon acid? We can do that. So let's see. So 3 carbon acid, 1 carbon alcohol. Can we name this? This will be methyl propanoate. You can also do what? 3 carbon alcohol, 1 carbon acid. So let's see. So this right here is what? Propyl methanoate. So this is also an ester. Is this clear? 2 carbon, acid, 2 carbon alcohol. 3 carbon acid, 1 carbon alcohol. 1 carbon alcohol, 1 carbon acid, 3 carbon alcohol. Any other combination possible?
One carbon from the right, based on the second carbon.
1 carbon from the right?
Based on the third one.
Oh, all right, I get it. You mean a branched one? Like this? Yeah, so this will also be possible. The thing is that the only thing here is a 3 carbon alcohol and 1 carbon acid. Yeah, but here you are using which type of alcohol? Rather than using propan 1-ol, we are using what? Propan 2-ol. Because if you see, this is the carbon which has the OH and this is the alcohol. Yeah, so it will be propan 2-ol again, but it's the same thing, right? It's going to be a 3 carbon alcohol, 1 carbon acid. But it's the same thing, right? You'll call it what? This will be propyl only because it's a 3 carbon alcohol. Clear? Is this understood? Do you guys get it? Do you all get it? Yes? Any questions? No questions? Did you guys get? 4, 5, okay. So let's try. Let's see the first one. You will make a main chain of 5. Make a pent 1-ene. Yes. Then you shift the double bond on carbon number 2. This right here becomes what? Pent 2-ene. Let's see, can we shift it on carbon number 3? If you shift it on carbon number 3, it again becomes what? Pent 2-ene. You've already drawn it. Why? Because now you will number from this side. When you number from this side, alkene comes on carbon number 2 and 3. You will pick the smaller number and this will be pent 2-ene, but you've already drawn it. Now you will shorten the chain. You shorten the chain, make a main chain of 4 and put the alkyl, let's say, on position number 2. So this becomes what? 2-methyl but 1-ene. Now, can you have a 3-methyl but 1-ene? Which is the most important functional group, alkyl or alkene? Which should get the least number? Alkene. So you will number from this side 1, 2, 3. So can we call this 3-methyl but 1-ene? Yes. Now let's change the double bond on position number 2. Let's make a but 2-ene. And let's put the CH3 over here. What do we call this? 2-methyl but 2-ene. Can we have a 2-methyl but 3-ene? Let's see. So if you think this is going to be 2-methyl but 3-ene, no, you will number from this side. It will be 2-methyl but 2-ene. I mean, this can't be 3-methyl but 2-ene. This will be 2-methyl but 2-ene. Clear? Now we have to further, let's say, shorten the chain. If you further shorten the chain, how many carbons do we have to put now? 2. You'll be like, oh, you can't put 2 methyls over here. How about we put a ethyl over here? Yes, we put a ethyl. The longest chain becomes 1, 2, 3, and 4. This is not 2-ethyl propanene. The main chain is now again 4 carbons. And this will be what? Alkene will get the least number. So carbon 1, carbon 2, 3, and 4. So this is what? 2-methyl but 1-ene. You've already drawn that? Yes? Any other isomer that you think we can make from this? So this is not an isomer, we've already drawn it. So how many isomers did we get? 5. Is this clear? Do you all get it? Kids online, do you get it? Now we will be starting with stereoisomerism. Let's start with what were structural isomers? They had the same molecular formula but different structural formula. What were the types? Chain, positional, and functional. Which ones were functional? Aldehyde and ketone, acid and ester, alkene and cycloalkane, alcohol and ether you don't really have to bother with, right? Now let's see stereoisomers. Stereoisomers, we've already defined it earlier when we were doing isomerism. They have the same molecular formula. They have the same structural formula, but different arrangement in space. So they have different arrangement of atoms in space. So they are isomers with the same molecular formula, same structural formula, but different arrangement of atoms in space. There are two types of stereoisomers. We have the geometric isomerism, which is also known as Cis Trans, and we have optical isomers, which are also known as enantiomers. Yeah. So let's see Cis Trans or geometric isomerism. Now, what are geometric isomers? For geometric isomerism, two criteria must be fulfilled. How many criteria? Two criteria must be met. And what are the two criteria? Let's see. This is also known as, by the way, what? Cis Trans Isomerism. What do we call this? Cis Trans Isomerism. So two criteria must be met for geometric isomerism or Cis Trans Isomerism, which are, you must have a carbon-carbon double bond. What should you have? A carbon-carbon double bond, not just any double bond, a carbon with a carbon. Yeah. So this is also known as Cis Trans Isomerism. And how many criteria must be met? Two criteria must be met for this type of isomerism. The first is, you must have a carbon-carbon double bond. Yeah. So there must be a carbon-carbon double bond. And the second criteria is, on each carbon, there must be two different atoms. So there must be two different atoms or groups of atoms. So what did I say? You must have a carbon-carbon double bond, and on each atom, each carbon atom, you must have two different atoms or groups of atoms attached. In this case, we will say that it will show which type of isomerism? Cis Trans or geometric isomerism. Let's see. Let's see an example. So you have C double bond C with an H with a Cl with an H with a Cl. The first criteria is you must have a carbon-carbon double bond. Do we have that? Does this have a carbon-carbon double bond? Yes. So the first criteria is fulfilled. The second criteria is, on each carbon, you must have two different atoms or groups of atoms. Do you see on this carbon you have two different atoms, H and Cl? Let's look at this one. On this carbon also, do you see you have two different atoms, H and Cl? So on each carbon, do you have two different atoms? Yes. So can this show cis trans? Yes. Now how will we know what is cis and what is trans? If both the carbons have something common or a similar atom. Do you see they have similar atoms on each carbon? This also has a H, this also has H, this also has a Cl, this also has. So if similar atoms are on the same side of the molecule, the isomer will be cis. So if similar atoms, do you see hydrogen, hydrogen is similar? Do you see it's on the same side on the top? Or HCl, Cl, they are similar, they are on the same side as well. So if similar atoms are on the same side of the molecule, then the isomer is what? Then the isomer is what? Cis isomer. What will we call this? Now first, let's name this. This is what? 2 carbon main chain. On carbon 1 and 2, we have a chloro. What will we call this? 1, 2 dichloroethene. Yes? 2 carbon alkene. On carbon 1 and 2, we have a chloro. So we will call this 1, 2 dichloroethene. Now on this, you have, what is the structural formula? Let's see. Structural formula is CHCl, double bond, CHCl. Yes. What's the molecular formula? C2H2Cl2. And I told you which isomer is this? Cis isomer. So what will we call this? We will call this cis 1, 2 dichloroethene. Now you'll be like, Miss, what is the trans isomer then? How do we make the trans? For the trans isomer, similar atoms must be on opposite sides. If similar atoms are on the same side, what do we call this? Cis. If they'll be on opposite sides, we will call it the trans isomer. Let's see. So you put one H here, Cl here. Let's put the H here now. Do you see the similar atoms are on opposite sides? This will be the trans isomer. When similar atoms are on the same side, we call it cis. When similar atoms are on opposite sides, we call it trans. So if similar atoms are on opposite sides, it is the trans isomer. Now you'll be like, Miss, the cis and the trans, I mean, isn't it just if I try to rotate the trans isomer from the double bond, from the middle, if I just rotate half the molecule, it will become cis, or the cis will become trans. If I just rotate, they're connected via a double bond, right? So if I just rotate it from the double bond, won't it become the same thing? But that's the thing. Rotation around the double bond is very difficult. It is not possible. Because the double bond is strong, it has a sigma and a pi, so you can't rotate from the double bond. You can't flip the molecule from the middle. All right. So these are isomers. Why? Let's see. Let's see the name. This is also what? 1, 2 dichloroethene. Let's see the structural formula. CHCl, CHCl. Do you see the molecular formula will be C2H2Cl2? Do you see the molecular formula is the same? Structural formula is the same. But they are still what? They are isomers of each other. One is cis, one is trans. And they are formed. Why? Due to limited rotation around the double bond. And do you see here? Molecular formula is the same. Structural formula is the same. They are isomers because of the position of atoms. In cis, both similar atoms are on the same side. That's why it's the cis isomer. In trans, the similar atoms are on opposite sides. It's the trans isomer. This is a very lame way of remembering the cis and trans isomer. Not remembering, but just identifying the cis and trans. All right. So let's see that lame way, which I'm sure you guys can very easily connect with. All right. You'll very easily remember it because you know what I'm implying, right? Okay. No. So let's see. Now, very lame way of remembering it is if you have a cis isomer, yeah, and also guys, just the way of remembering same side, sir, right? Same side, cis. Opposite sides, trans. If you have to identify the isomer, whether it's cis or trans, you go from the similar atom to the other similar atom. Let me take hydrogen, hydrogen, all right? So you go from the similar atom to the carbon, to the carbon, to the other similar atom. Whenever you have a cis isomer, you get a boat. Do you see you kind of get a boat? Yeah. I mean, if you want to go from this similar atom to this similar atom, it's an inverted boat, but whatever, it's a boat. Yeah. So the cis isomer kind of looks like a boat. Yeah. On the other hand, the trans isomer, I'm not writing this in my notes. If you want to make a note, you can make it. All right. I'm not writing boat and chair in my notes. All right. And please, if they ask you why is this a cis isomer, don't say because it makes a boat. All right. You will say because similar atoms are on the same side, not because it's making a boat and a chair. All right. Okay. Now you have, let me take chlorine here. Similar atom, chlorine to carbon, to another chlorine. Did you see it makes a chair, a dental chair where you have a patient like this? Yes? Yeah? So trans isomer will make a chair, cis isomer will make a boat. That's how you identify it. In cis isomers, similar atoms are on the same side, and in trans, similar atoms are on opposite sides. Same molecular formula, same structural formula, but what is different? Arrangement of atoms is why we call them cis and trans isomer due to limited rotation around the double bond. Is this clear? Do you understand this?